You can see it now. Hello, everybody, and welcome back to the main goal that will never die design my own AI chip, starting from the very scratch, starting from the basics of designing and writing simply chip, and then graduating gradually up to really making the um, architecture that covers how a neural network work in the chip itself. So thank you so much for first of all, and without further speaking, let's go for sharing the discussing again part of the basics. So we are in a good stage. So we have already covered the basic of programming system Verilog in order to design a chip. We have talking about combinatorial design, and now we are covering last but not least the sequential part of it, which the clock will be part of the game. So dive deeper into the
You are building the control logic for your calculator model, and now you have to decide how the circuit should react to inputs. Should the calculator update instantly when an operand changes, or only when the clock ticks?
only when the clock ticks. This is a sequential, right? So sequential is you perform tasks only when the clock ticks.
System Verilog provides powerful always blocks for describing both combinational and sequential logic. Still, the real question is, how do you choose the right kind, structure the sensitivity list, and use the correct assignment type so your calculator behaves exactly like a real hardware? In this video, we will break down the always block model, both combinational and sequential logic in System Verilog. See how sensitivity list determines when your calculator logic reacts to input changes or clock edges. Compare blocking and non-blocking assignments and learn when each is appropriate, especially for arithmetic operations and register updates inside the calculator data path. Finally, we'll walk through small examples, including the flip-flop structure used to store calculator inputs and results. So by the end of this video, you'll be able to differentiate between the always comb, always FF, always lash, and identify when each applies in your calculator design. Construct correct sensitivity lists for combinational and sequential logic. Apply blocking assignments for combinational logic and non-blocking assignments for sequential logic, avoiding race conditions in arithmetic and logic operations. Then we implement flip-flops, resets, and control behavior for calculator model using clean, synthesizable always blocks. Earlier, we talked about the difference between combinational and sequential logic. Combinational logic reacts immediately to its inputs, while sequential logic relies on a clock and stores states using flip-flops. As a result, sequential circuits update only on specific clock events. So to describe this kind of behavior in System Verilog, we use procedural blocks. The most common is the always block. Anytime a signal in its sensitivity list changes, the statements inside the block run in order, one after another. So how do sensitivity lists actually? Let's break it down. So inside an always block, your code loops continuously, but in hardware, nothing should change unless an input changes. That's what the sensitivity list models. So for example, a D flip-flop updates only on a positive clock edge. Here, only a rising clock edge triggers the block. Anything else is ignored, exactly like real hardware. In our FIFO sum model, we use a sequential always block to update the write and read pointer. Just like D flip-flop example, the sensitivity list tells system Verilog exactly when the block is allowed to run. This style lets the flop reset instantly, even between clock edges. So here is what the sensitivity list means. Positive clock edge. So the block only updates on the rising edge of the clock, which models the flip-flop that stores our FIFO pointers. Then positive edge of reset. The block also triggers immediately when reset goes high. Its internal state, asynchronously, even between clock cycles. This sensitivity list ensures the FIFO behaves like real hardware. The register updates only on clock edges under normal operation, but can still be reset instantly when the reset is asserted. Now that we understand when block executes, let's look at how. So we have the blocking versus the non-blocking assignments. In System Verilog, we use two types of assignments. Blocking, here the update happens right away. Think of it like basic combinational logic. Change the inputs and the output changes immediately. But for non-blocking, we use this sign. So the update is scheduled and all updates happen together at the end of the time step. So this is how real flip-flop behaves. Non-blocking assignments, they make sure every flip-flop updates at the same time, so you don't accidentally overwrite values or create weird feedback loops. Let's look at a practical example to see why this matters. Imagine you have two score counters, A and B, and every clock tick you want to swap their values. Now, with non-blocking assignments, it works perfectly. Both A and B values first, then swap at the same time, just like two real flip-flops. But if you use blocking assignments, the first line will immediately overwrite A, and the second line will use that new value, meaning the swap never actually happens. So non-blocking keeps everything synchronized and prevents those kinds of mistakes. The always block is the foundation of sequential logic design in system development. So by mastering sensitivity list, you control precisely when your logic responds, whether to curve edges, resets, or input changes. And by using the right assignment type, whether it's blocking for combinational, non-blocking for sequential, you ensure your